hello everyone. I am Subhodeep from IIIT Allahabad, and firstly, I would like to thank the organizers and the session chair for giving me this opportunity to present my work here. I will be talking about the cosmic censorship, strong cosmic censorship conjecture, with a particular focus in anti-de Sitter spacetimes. And as we will see, the strong cosmic censorship conjecture deals with physics that lies behind the event horizon of the black holes. So when I talk about tests, I am talking about probing the uh, doing theoretical checks that prove the validity of Einstein's theory of gravity itself. It's best to start at the very beginning by asking a very simple question. So let's say our observer were to fall into a short-shell black hole. So what would he experience or see? Well, he would nothing much really. He would just go and hit the space-like singularity that exists inside a short-shell black hole. What this means is that the space-time cannot be extended beyond this space-like the surface. But the situation is very different when we deal with black holes with multiple horizons. For example, the RN black hole. So in RN black hole, that has as a outer horizon, that is the event horizon, and an inner horizon, which are actually Cauchy horizons. So there is a possibility that an observer falling into a black hole can cross the inner horizon, avoid hitting the timeless singularities, and emerge in another universe. Now, this is a catastrophe. This is because that this implies that the space-time can be extended beyond the Cauchy horizon. Or in other words, okay, the motion of this observer cannot be alone predicted by some initial data that is described in our universe. This signals a breakdown of determinism in general relativity. And this is a serious issue. And to rescue determinism in GR, Project Penrose suggested what is now known as the strong cosmic censorship conjecture. He said that the Cauchy horizon should be unstable. Basically, when a perturbation falls inside a black hole, it gets highly blue shifted near the Cauchy horizon and renders it singular. Now, the issue is actually much more subtle. The infalling perturbations, okay, they get backscattered and generates the outflux. And it was shown that as a result of this, the mass parameter of the black hole actually diverges at the Cauchy horizon, giving rise to the phenomenon known as mass inflation. It was further shown that these singularities are weak null singularities. And this eventually led to a reformulation of the strong cosmic censorship conjecture by QCW. We will discuss these things in more detail as we go along. But to the best of our knowledge, SCC is pretty much respected in asymptotically flat spacetime, and this has been backed by numerous mathematical and numerical analysis. Although, last week a paper appeared that studied SCC violation in 3D black strings, and this appears to be a exception that, as with regards to the violation of strong cosmic censorship in asymptotically flat spacetime. Now, before moving on, I would just need to comment that what this means physically. So, physically, perturbations outside the horizon decay following Price's law. Okay, they have power law tables. And therefore, this decay is slow enough compared to the exponential rise in the blue shift instability near the Cauchy horizon. And there's a competition between these two. And as a result of this slow decay, okay, the perturbations have opportunity to become extremely blue shifted at the Cauchy horizon. And this sort of rescues cosmic censorship in asymptotically flat spacetimes. In de Sitter spacetime, the situation is different. In de Sitter spacetime, the perturbations decay exponentially outside the event horizon. So there is a possible hint of violation of cosmic censorship in de Sitter spacetime. It was shown that in near extreme RNDS, okay, SCC is violated classically, but surprisingly enough, curl DS respects strong cosmic censorship. This is because there is always a family of quasi-normal modes that decay slowly enough in curl DS. And a recent result for RNDS suggests that quantum effects or semi-classical effects ultimately does restore cosmic censorship. Naturally, this line of questioning leads us to focus on anti-de Sitter spacetime, the main component of this talk. Okay. Now, the situation in ADS is something like this. We know that perturbations decay very slowly in ADS4. This is basically due to the stable trapping phenomena. Basically, since we have a reflective time-like boundary in ADS, okay, some of the perturbations get trapped, and this actually gives rise to a inverse logarithmic decay. And this there are hints that this might lead to a strengthening of the singularity at the Cauchy horizon. It has actually shown that in ADS spacetime, it is still possible to extend the metric across the Cauchy horizon. Okay, but the singularity is a weak null singularity. That is, although the metric can be extended across the Cauchy horizon, it will not have locally square integrable Christoffel symbols. And therefore, one can say that it actually respects the modern reformulation of the strong cosmic censorship conjecture. Furthermore, by studying the freely falling observers, it can be established that although the tidal forces are infinite near the Cauchy horizon, the tidal distortions remain fine. Now, if we ask that what is the situation for a BTZ black hole? A BTZ black hole is a solution of the Einstein's equation in 2 plus 1 dimensions with a negative cosmological constant. And it is not immediately clear if the results that hold for ADS4 will also hold in ADS3 or in a BTZ spacetime. This is because in a BTZ spacetime, the stable trapping phenomena does not exist. And the result, it was found very recently in 2019 that a near extreme BTZ black hole actually violates strong cosmic censorship. The result, surprisingly enough, hinges on a remarkable coincidence. Okay, so you can set up the scattering problem inside the black hole as well, and you can find out something that are like analogous to quasi-normal modes. Okay, these are known as interior quasi-normal modes, and it was found that some of the interior quasi-normal modes match the quasi-normal modes outside the black hole, the exterior quasi-normal. And this results in a very unique result that the behavior of the scalar field becomes actually bounded near the Cauchy horizon when the black hole is near extremality, resulting in a violation of HCC. Interestingly enough, quantum effects apparently do not save HCC as well. Although there are two ways to one way to sidestep the problem. So Emperor and Tomasevic suggested that maybe going beyond linear order might rescue HCC. Now we ask the question that what is the experience of an infalling observer as a complementary to the as a complementary analysis following Diaz et al. Study. Our starting point is a remarkable coincidence, that is, to put it in precise terms, the BTZ black hole, which have two families of quasi-normal mode, the prograde mode and retrograde mode, and one can show that a family of the interior quasi-normal modes near the right Cauchy horizon actually coincides with the prograde mode. So interestingly enough, the behavior of the non-smooth behavior of the scalar perturbation near the Cauchy horizon will be governed by the faster decaying retrograde mode. Then once we can model the infalling perturbations, okay, or the infalling null dust using this retrograde mode, then what we can show is that when this null dust gets scattered near the backscattered near the Cauchy horizon, it gives rise to outflux. The precise nature of the outflux is not important, but the presence of the outflux basically divides the entire spacetime into two regions, which are Boito-like, which are described by Boito-like solution, and one can then match the metric across this thin null shell and write down what is known as the expression of a mass parameter, which is found to inflate or grow exponentially or grow in a very weird way. So this is the essence of the OD model. So doing so, we find that the mass parameter does diverge near the Cauchy horizon, provided the black hole is far from extremality. However, if it is near extremality, the black hole the mass parameter seems to divergence does not seem to be powerful enough to enter the Cauchy horizon singular. So our model is essentially a toy model, and interestingly enough, this toy model captures a lot of the intricate dynamics that was predicted by the study carried out by Diaz et al. Interestingly enough, that our model gives the correct behavior of the stressed energy tensor as well. We name this phenomena anomalous mass inflation because, interestingly enough, it is the faster decaying quasi-normal mode that governs the behavior of the influx. Moreover, we were able to write down an exact mass inflation solution that helped us to study the experience of an infalling observer. We were able to characterize the singularity as a weak null singularity, which is to say that tidal distortions remain finite even the tidal forces diverge. Furthermore, we were able to find a bound on the spin parameter of the black hole beyond which SCC will be violated. And we were also able to argue that the quantum stress tensor has to have a diverging behavior that is as bad as that of the classical singularity. Now, moving on, or rather moving down, we focus now on 1 plus 1 dimension. Now, in 1 plus 1 dimension, you have to add a dilaton field to your gravity theory. And these are basically uses theoretical laboratories to test various aspects of GR, such as the information loss paradox. Notably, Jackie-Taitagram gravity is extremely popular. Uh, this is because in the near horizon limit of near extreme black holes, we recover this ADS2 geometry. We take one such model, which permits a black hole solution with Cauchy horizons.
Well, you have 5 minutes. Okay.
Yeah, thank you. Which is actually equal to the dimensional reduced BTZ black hole. And to study the violation of SCC, we follow the analysis of Diaz et al. But there's one caveat. We have to generalize the Klein-Gordon equation in a particular way. So basically, we have to include a coupling between the dilaton field and the matter perturbation. This is indicated by this H of phi thing sitting inside in the Klein-Gordon equation. When following Diaz et al., we were able to calculate the QNM and show the coincidence that we talked about occurs in this 1 plus 1 dimension as well. Set up an initial value problem and show that the scalar field is smooth near the Cauchy horizon for a near extreme black hole, and show that classically SCC is violated. But a very simple calculation invoking the stress anomaly is able to show that semi-classical effects ensure that SCC is respected in 1 plus 1 dimension, ADS spacetime. Finally, I will just end right now. So what lies in the future? Okay, so classically, RNADSO seems to respect SCC if the mass inflation model is well understood. However, there's a paper by Corsa and Balbin, not an old paper at that one, which says that quantum effects or semi-classical effects can modify the behavior of the mass inflation singularity. It can either strengthen it or weaken it as well. One way to check this would be to set up a quantum scattering problem following the work of Hollands et al. Or by following the works of Ori and his students. And one can rigorously answer this question. Okay, so if there's a quantum instability lying inside the charged ADS or black hole as well. We are investigating this right now. I am with Mustafizur Rahman, my supervisor, Sujit Bhattacharjee. And hopefully in the future, I might update you guys regarding this particular work. So that would be all. I am funded by DST ACIB, and I would be happy to take questions.